Hello, thank you very much for viewing this virtual presentation. My name is Jiang Qingye and I'm here to present our paper on the power of ARM64 in public clouds. This paper is jointly prepared by me, Dr. Yang Lee at Macquarie University, and Professor Alva Zomaya at the University of Sydney. In recent years, there is an increasing attention on energy consumption in the IT industry, with a heavy focus on ARM processors. Traditionally, ARM processors have been highly successful in embedded systems, including tablet computers and smartphones. In 2018, AWS announced the Amazon Graviton processor, which is a 64-bit ARM processor based on the Cortex-A72 microarchitecture. The Amazon Graviton processor is made available on EC2 as the A1 product family. In this paper, we evaluated the capacities of the Amazon Graviton processor using a combination of microbenchmark and case studies. And then we make comparisons to the Intel Xeon product family. In this paper, we conducted both microbenchmark studies and case studies. The microbenchmark includes single-thread tests and multi-thread tests. The test results reveal the advantage and disadvantage of the Amazon Graviton processor. The case studies included multi-tier web service, video transcoding, and terabyte-scale sorting. These tests were designed to evaluate the feasibility of using the Amazon Graviton processor for horizontally scalable compute-intensive workloads. Now let's first take a look at the benchmark studies. The benchmark suite we use is UniqueBench. In UniqueBench, there are 12 individual tests, and they are described in details in this table. Each test was designed to evaluate the performance of a particular component on a computing system. For example, the dry-stone test evaluates integer computation performance, while the whetstone test evaluates floating point computation performance. Our tests were conducted on Amazon EC2, and we use the A1, I3, and M5 EC2 instance families. This table describes the configuration of each instance type, including the number of vCPU cores and the amount of memory. The majority of our benchmark tests are conducted on A1 4x large and I3 16x large running on dedicated hosts. These two instance types support an undocumented feature which allows performance analysis by accessing specific processor registers. Apart from the number of vCPU cores and the amount of memory topology also has a significant impact on performance. In this table, we describe the memory topologies on both A1 4x large and I3 16x large. The A1 4x large instance has a larger L2 cache, but has no L3 cache. I3.16x large has a smaller L2 cache, but has an additional L3 cache. Since A1 4x large and I3 16x large have different number of vCPU cores and different amount of memory, we need to find a way to make a fair comparison using the index scores reported by UniqueBench. In UniqueBench, each point in the index score represents a fixed amount of work. Therefore, we can calculate the cost of doing the same amount of work in terms of performance counters. This is described in equation 1. Further, we use relative score to represent how one system performs as compared to another reference system. This is described in equation 2. This figure describes the single-thread benchmark results. In all individual tests, the index score on A1 is smaller than the index score on I3. With I3 as the reference system, in the best case, A1 achieves a relative score of 86% in system core overhead. In the worst case, A1 achieves a relative score of 13% in context switch. This figure presents the coarse analysis of the single-thread test results. Looking at subfigure A, A1 4x large needs more instructions to achieve a point in all tests, except for whetstone and Excel throughput. Looking at subfigure B, A1 4x large needs more CPU cycles to achieve a point, except for whetstone and Excel throughput. Then we look at subfigure C. I3 16x large achieves higher instructions per cycle in all tests except for pipe throughput and system core overhead. Now let's look at subfigure D. A1 4x large encounter more cache misses to achieve a point. This test result suggested that memory topology has the biggest impact on the performance difference we observe here. Although memory access is fast, it is still relatively slow as compared to the speed of the processor. This is commonly known as the memory wall. When the processor requests data access, it checks the cache, which is faster, before accessing DRAM, which is slower. If the data is present in the cache, this is called a cache hit. The computation can be speeded up by not accessing the slower DRAM. If the data is not present in the cache, this is called a cache miss. In this case, the computation is slowed down because the data needs to be fetched from the slower DRAM. This is the multi-thread benchmark results. In most tests, the index score on A1 4x large is significantly lower than I3 16x large. Well, this is reasonable because I3 16x large has 64 vCPU cores, while A1.4x large has only 16 vCPU cores. However, in all three file copy tests, the index score on A1 4x large is higher. This suggests that file copy performance is controlled by disk I/O capacity. In the single-thread test, the disk I/O capacity is not fully utilized. In the multi-thread test, the disk I/O capacity becomes fully utilized by the combined workload. Since I3 16x large has much more worker threads, there exists a higher level of competition for disk I/O among the worker threads. This led to the increased level of performance degradation. This figure presents the coarse analysis of the multi-thread tests. This is somewhat similar to the coarse analysis in the single-thread tests. Due to time constraints, I am going to skip a couple of figures in this presentation. This figure presents the system benchmark index score for all instance types in the A1 and I3 product family. In the single-thread tests, there exists only some insignificant difference in the index scores achieved on bigger instance types. This is reasonable because the test thread only utilizes one of the many vCPU cores on the system. In the multi-thread test, when the number of vCPU cores doubles, approximately 40% to 60% increase in index score is observed. Now let's take a look at our case studies. Multi-thread web service is a typical use case in public clouds. A multi-tier web service usually includes the following components: a web server as the front end, a database server to persist user data, and a cache layer for session sharing and caching database query results. And in this figure, we present the performance of these individual components, including serving static web pages, serving dynamic web pages, in-memory caching, and making queries to relational databases. And this figure presents the performance of a multi-tier web application. The M5 instance achieved the best performance in the integration test. This is expected considering its outstanding performance in all component level tests. After that, I3 achieved relatively better as compared to A1. Apart from performance, we also need to consider the cost to achieve the desired performance. And the figure on the left-hand side presents the number of requests that can be achieved with 1 US cent in the integration test. Surprisingly, A1 achieves higher requests per cent than M5, and I3 achieves much smaller number of requests per cent as compared to A1 and M5. Video transcoding is another common use case for websites. And here we are talking about a video sharing service. When the end user uploads a video to the service, the video is stored in an S3 bucket, and then a record is written to the database, and a transcoding job is published into a message queue. The uploaded video are then transcoded in the background with a batch processing system. And then the transcoded video are uploaded back to the S3 bucket. This figure is the architecture of the video transcoding application used in our case study. As shown in the figure on the left-hand side, the transcoding speed increases when the EC2 instance becomes bigger. There is roughly a linear relationship between the transcoding speed and the number of vCPU cores. For the same instance type, the A1 product family has the slowest transcoding speed, while the I3 product family has the fastest transcoding speed. This suggests that video transcoding is more memory intensive than CPU intensive, because I3 has slower CPU clock rate but more memory than M5. M5 has a faster CPU clock than A1, and it achieves better performance in transcoding as compared to A1. But if we look at the figure on the right-hand side, for all three instance types, transcoding speed increases linearly with the addition of more worker nodes. Although A1 has the slowest transcoding speed per node, such linear scaling behavior allows it to achieve the desired level of performance by simply adding more nodes into the worker fleet. This figure presents the cost of transcoding 1,000 video clips on different instance types. The I3 product family has the highest transcoding cost. The A1 product family has some modest cost saving as compared to the M5 product family. And finally, we use the TerraSort application in the Hadoop examples to perform sorting on a 1 terabyte dataset on Hadoop clusters. The figure on the left-hand side presents the execution time of sorting 1 terabyte data. For all instance types, the execution time decreases when the number of nodes increases. The execution time on i3 and M5 are approximately the same. The execution time on A1 is significantly greater. The figure on the left-hand side presents the execution cost of sorting 1 terabyte data. i3 has the highest execution cost, followed by M5. A1 has the lowest execution cost. Now let's take a look at our conclusions. Well, in this paper, we studied the performance characteristics of the Amazon Graviton processor with comparison to Intel Xeon processors using a combination of microbenchmark and Linux performance counters. We demonstrate that the lack of L3 cache and the slower memory access speed can prevent Amazon Graviton processor from achieving higher performance for compute-intensive workload with intensive demand on memory. We use multi-tier web service, video transcoding, and terabyte scale sorting as case studies. In our large-scale evaluations, the largest cluster include 1,600 vCPU cores, which is by far the largest ARM64 cluster that has been reported. The single node performance of the A1 product family is not as good as the single node performance of the i3 and M5 product families. However, satisfactory processing capacity can be achieved by practicing horizontal scaling. We also demonstrate that the A1 product family achieves the same price performance in multi-tier web services, up to 37% cost saving in video transcoding, and up to 65% cost saving in terabyte scale sorting. And this opens the door for further optimization for workloads with both cost and deadline constraints. Again, thank you very much for attending this virtual presentation.